Hi, let's continue discussing a few more problems from Poisson brackets. All right, the problem that we are going to discuss first has been asked in one of the previous NET JRF exams. So let's see how we can solve this. So the Hamiltonian of the system is given here. A system is governed by the Hamiltonian given by this term, okay, where A and B are constants and Px and Py are momenta conjugate to x and y respectively. For what values of A and B will the quantities Px minus 3y and Py plus 2x be conserved, right? So we are asked to find the values of A and B such that these two quantities are conserved. Okay. Now, if you look at this, you see that there is no explicit time dependence for these quantities, all right? Which means that if we say that Px minus 3y is conserved, this means that the Poisson bracket of Px minus 3y with h with Hamiltonian has to be equal to 0. Similarly, from here, if this quantity is conserved, we can say the Poisson bracket of Py plus 2x with h is equal to 0. Okay, so we construct these equations, use the fundamental Poisson brackets, which are x with Px is equal to 1, etc. Similarly, Pi with Pj are all equal to 0. Similarly, Qi with Qj are all equal to 0. And this we can write generally as Qi with Pj is equal to delta Ij. Right? We can use just these fundamental Poisson brackets and solve this problem. Okay. All right. So what I want to emphasize is that in most problems we don't have to go to the definition of the Poisson bracket. All right. We can just use the fundamental Poisson brackets. So first, let's demand the first condition. We have said that Px minus 3y is a conserved quantity. Okay, then obviously, as I said, Px minus 3y with h, that Poisson bracket has to be equal to 0. So we write it down, we write down the Hamiltonian here. Alright. Now, a trick to simplify such problems is to look for only the non-zero Poisson brackets. Alright, you look only for the non-zero Poisson brackets. You don't have to expand it all in the beginning and then find them equal to 0. Just by inspection we can find out the non-zero Poisson brackets because we know the fundamental Poisson brackets. Alright, so let's take this term. Alright, there's a Px here. Alright, what's the Poisson bracket of Px with Px? It's 0. Px with y is also 0. Right? Similarly, y with Px 0, y with y is also 0. Right? So we see that the contribution from this term in this equation is 0. So we don't have to expand all this. We can just write down only the second term. Right? The only non-zero contribution to this Poisson bracket comes from this term. All right? Why? Px with Py is 0, fine, but there's this Px with x. The Poisson bracket of Px with x is 1. Okay, so that's the only thing that's non-zero. So immediately let's drop this term because even if we expand and do it, we'll get Poisson brackets which are 0. So let's discard it immediately and reduce this to Px minus 3y with half Py minus Bx whole square is equal to 0. Okay. Now there are different ways, there are different number of ways to do this. One way to do this is to use this formula u with v square, as we said, is 2v multiplied by u comma v. Right? We have seen this relation. I told you that this would come in handy, so let's use this. You can solve it in the way you like. Okay, so that's exactly what we are doing here. First, I pull this half outside, okay, because the constant can be pulled outside. That half appears here. Okay, and then comes this 2v. This is v square, so you have got a 2v, that is 2 py minus bx, and then we have got px minus 3y comma py minus bx. Okay. So this is Py minus Bx, which sits there, and let's look at only the non-zero Poisson brackets. Px with Py is 0, Px with x is 1. Okay, so there is this minus there. Similarly, y with Py or y with Py is also equal to 1. Alright, sorry, Px with x is actually minus 1. Alright, we know that x with Px is equal to 1, so Px with x is equal to minus 1. Okay, so that minus would say that from here we get a b, right, and from here we get a 3, minus 3, because y with Py is 1, so b minus 3 here, that's it. Okay, that's quite easy, and we see that this term appears in the Hamiltonian. All right, we don't set that equal to 0, so if this term has to be equal to 0, then b has to be equal to 3. Okay, b has to be equal to 3. We can look at the solutions immediately. If there are any options with b equal to 3, we see that there's only one option, so we can choose that immediately. Right? But for the sake of getting more practice, I ask you to do the rest of it as a homework. Okay? So we have got py with 2x, all right. You can check this Poisson bracket, py plus 2x with h is equal to 0. Demand that and see that a becomes minus 2. The steps are very similar. It's exactly the same too, all right. So you can do the rest of it. Here we are asked the value of the Poisson bracket a comma b. Right, so you can use this distributive rule and the fact that you can pull the constants out, okay, and the linearity property. So we can just write this. This is so remember that p1 with q1, okay, p1 with q1 is 1, p2 with q2 is also 1, but the others are 0, p1 with p2 etc. 0. So let's first look at this term, all right. Let's first look at this term and let's combine with both these terms. Right. So here there is a constant c, here there is a constant a, we can pull them out, so it's ac, okay, and p1 with q1, all right. We can also look at this Poisson bracket, but we see immediately that this is 0 because p1 with p2 is 0, okay. So we take just that term. Similarly from here we pull out this b, okay, and you check this term, we see that it's 0 because q2 with q1 is 0, right. So we can take this outside, it's bd and then q2 with p2, okay. p1 with q1 is minus 1 because q1 with p1 is 1. That's a fundamental Poisson bracket, all right. So it's minus ac plus bd. So the answer is bd minus ac. Such problems you can do. Here the Lagrangian is given. Find the Poisson bracket theta with theta dot. We are asked the Poisson bracket theta with theta dot. All right. How do we do this? So if you are going to use the fundamental Poisson brackets, we know the fundamental Poisson brackets between the coordinates and the momenta, right? The coordinates and the momenta, x with px, etc. But here we have got a theta dot. Right? So what do? We find the conjugate momentum and write this theta dot in terms of p theta. Okay? We write this theta dot in terms of p theta. Right? That's the trick that we need to do. So we look for p theta is dou L by dou theta dot, which is ml square theta dot. So from here we find that theta dot is equal to p theta divided by ml square. Okay, all right. So we can either substitute for theta dot. So let's do it like this. Theta dot is equal to p theta divided by ml square. Okay, so theta with theta dot is actually equal to theta 1 by ml square, which can be pulled out of the Poisson bracket, and theta with p theta. Okay, so theta with p theta is 1, so this is 1 by ml square. Okay, that's one way of doing it, right? So the thing in the notes is slightly different, so I just want to demonstrate that there are so many different ways to solve such problems. Here the Lagrangian is given. Find x dot with y dot. Okay, the Poisson bracket x dot with y dot. I leave it as an exercise for you. Okay, this problem I leave as an exercise for you. Right. So you could proceed exactly in the same manner. You can get rid of all x dot, y dot, and z dot in favor of px, py, and pz. Okay, that's what you will do, and then you can use the fundamental Poisson bracket relations. Okay. The next problem is evaluate the Poisson bracket a dot r comma p. Okay. Now how do we do this? We have talked about this p vector, right? We are given p vector here. So what we can do is that we can actually evaluate the Poisson bracket for one component first, and then look at the then we can find out the other things. Okay. So let's just write it abstractly in this way. We can write this as a dot r is actually a I r I. Okay, with pj. Right. What does this mean? This means there's a summation over I. As I said, we will be using Einstein summation convention. Okay. This is AIRI with pj. Now we have written this in component form. Okay. We have written this in component form. Okay. Now we can pull this AI outside. So this is simply RI with pj. Okay. So this is the convenience of using the index notation and using the Einstein summation convention. And we know that RI with pj. Okay. Ri with pj is actually delta ij. That's one of the fundamental Poisson brackets. Okay. So when you do such problems, you have to remember that once I have used this I as a dummy index here, I should use a different index here. Right? You cannot repeat the dummy index here also, because that would mean that we are making some sort of a summation, etc., which would confuse things. All right. So you use only a dummy index. This is known as a dummy index because it's just a prescription for you to sum over all values of I. All right, that's why it's called a dummy index. Okay? It could very well be k or m or anything, because whatever it is, this when it is repeated, it's a prescription to sum over 1, 2, 3. K equal to 1, 2, 3. So the final answer will be the same. So it doesn't matter what you put here. Okay, but always remember not to repeat it again in a different context, okay, in the same expression. That's why I've used I here and j there. So Ri with Pj is delta Ij. So remember that there's a summation over I. Okay, there's a summation over I. What does this mean? This means that it is A1 delta 1j plus A2 delta 2j plus A3 delta 3j. I have summed over all values of I. All right, I takes values 1, 2, 3. Now what is this? What is this? All right. So we see that only one term in this will actually survive. Only one term will survive. That term for which I is equal to j. All right. Only one term will survive. That term for which I is equal to j. All right. If j is 1, the first term will survive. If j is 2, the second term will survive, etc. So that's the meaning of writing this thing as, if there is a summation over one of the indices of the Kronecker delta, you can simply write it as aj. Right? Because this is the only non-zero term. The only non-zero term in this is ai delta, okay, or let's say aj delta jj. All right. In this expression, I have written it for understanding. There is no summation. All right. So there is only one term in this whole summation that will survive, and for that value, you write the answer as aj. All right. So what do we see then? We see that a vector dot r vector with p vector. Sorry, we have taken one component. Pj is aj. Okay, this means that if it is px here, you have got ax. If you have py here, you have got ay, and if you have got pz here, you have az. Right. So what does this mean? This means that this whole thing will give you the components of the vector. Right, and of course there are the unit vector, etc. So you can simply write it as a vector. All right. So a dot r with p is equal to a vector. Okay. So such problems, more such problems are there. This one you can try by yourself. All right. A dot r with r. That's an exercise for you. Here we have got a dot r whole square with p vector. A dot r whole square with p vector. Okay. So the way I have done it here is like this. What is a dot r? Okay. A dot r is ai ri. Right. What is a dot r square? So a dot r square is, you take this sum and then multiply it. Okay. aj rj. All right. Remember that both these are a vector dot r vector. Both these are a vector dot r vector. I've simply used a different dummy index, I here and j there. All right. You shouldn't repeat the dummy index in different contexts. All right. That would confuse, and that's a mistake. Okay. So here the summation index is I, here the summation index is j. So that's what I have done. It's ai ri aj rj with pk. Summation over I and j are implied. All right. This is one way to write a vector dot r vector whole square. This constants can be pulled out. So it's ai aj with ri rj with pk. Now we can use the usual rule. If you have something like a b with c, we know that it's a comma c multiplied by b plus a multiplied by b comma c. That's exactly what we do here. It's ri multiplied by rj with pk and plus rj multiplied by ri with pk. Now we know that this is delta jk and this is delta ik. All right. So it's delta jk, delta ik. Now this means that there's a summation over both I, there's a summation over this I, and there's a summation over this j. Okay. And there's delta jk. All right. So let's talk about this term. All right. Because this is summation. This is aj delta jk. All right. This means that there's a summation over all possible values of j here. Okay. And the only term that would be surviving is the one where j is equal to k. So you get ak here. Right? So this means that this term is actually ak. So this is ai ak ri. Remember, this summation still remains. Okay. This summation still remains. All right. Similarly, from here we have got ik here. It's this thing. All right. It's ai delta ik. The only term that survives is the term where I is equal to k. Okay, that's what this Kronecker delta tells you, right? It tells us that the only term survives in this summation is the term where I is equal to k. All other terms are 0, right? So you can simply put I is equal to k here. So it's ak aj rj, right? It's ai ak ri plus ak aj rj, okay? And we see that this is ai ri is again a vector dot r vector. Okay, this is a vector dot r vector. This ai ri is a vector dot r vector. Okay, plus, and here this aj rj is also a vector dot r vector. So you have got ak a vector dot r vector. All right. So remember, we have taken only one component of it. All right. We are asked p vector. We have taken only one component of it. So we see that these terms are exactly the same. So this is equal to 2 ak a vector dot r vector. But this is only one component. So if this is only the kth component of momentum, if it's the x component, then you would have ax here. If it's a y component, you would have ay here, and if it's a z component, you would have az here. Right? So we combine that. So that means that we have all three components of vector a. Right? When you do this vector here, and we get twice a dot r multiplied by a vector. Okay, so such problems have been asked before. So it's a good thing to practice with these indices. Here we have got a dot r with L, where L is the angular momentum vector. All right. So a dot r again we can write as a I r I, and this Lk. Okay. What's this Lk? We can write as epsilon k Lm RL Pm. What do we do that? Because we know that L vector is equal to r vector cross p vector. Right, L vector is equal to r vector cross p vector. Now the ith component of this cross product can be written as Lk. Let's say the kth component of this cross product can be written as, this is r cross p, or let's say the ith component. Okay, the ith component of this cross product, it could be the x component, y component, or z component, can be written using the Levi-Civita symbol. You could also take the determinant, but it amounts to the same thing. Right, this is epsilon I j k r j pk. All right, so it's a thing for you to remember. The ith component of a cross b. Okay, the ith component of a cross b. You know that a cross b is a vector. You know that a cross b is a vector. So it will have components. The ith component is given by epsilon I j k a j b k. All right. That's why I have written this Lk here. I am using only the kth component, even though there's a vector here. I am just checking with the kth component. All right. You could do for one of the components and then generalize. So this is a dot r Lk, and Lk I have written as epsilon k Lm. This is the kth component, so there will be a k here. L and m are dummy indices. Okay. Now I can pull these things out. These are numbers ai epsilon k Lm. All right. There are two terms here, Rl multiplied by Ri comma Pm. Right, because Ri with Rl is 0. Ri with RL is 0. The only non-zero term is Ri with Pm. That's why I can pull also this RL outside. Okay, that's why I have all these terms here. Actually, I have taken only the non-zero Poisson bracket. There should be two terms here. Actually, there should be one more term here, which involves Ri with RL. Okay, that's 0. That is already 0. I'm not writing any 0. Yeah, I'm taking only the non-zero Poisson brackets. And what's Ri with Pm? Ri with Pm is delta Im. Now we look where the summation appears, all right? So we can take it here. So this is Ai delta Im. You can think of it as Ai delta Im. That means it is Am, because it's a summation over I, and it will, the only value that survives will be the one for which I is equal to M. So that's why I write it as M here. So you have got Am, RL here, and epsilon KLM. And again, what's epsilon KLM RLAM? This is equal to, I can write this as epsilon, yeah, this is fine. This is actually, as we said, the kth component of R cross A. This is the kth component of R cross A. Alright, this is the kth component of R cross A. Am I right? Because the kth component of R cross A, we can write using the Levi-Civita symbol as epsilon KLM RLAM. Okay, that's exactly what we have here. You remember this definition, right? So this is only the kth component. If you take the kth component of angular momentum, you get the kth component of r cross A. So if you put the full vector, we get the full vector here. So it's r cross A. This is an important result. Okay, you might be using it somewhere. A dot r with L is equal to r cross A. Okay, it's r cross A. It could be asked, right? Now this one, I leave it as an exercise for you. This one, I leave it as an exercise. Okay, it's we can use the results in the previous problem, right? You can use the results or the things that I told you in the previous problem and also do this one, right? So in the end, we'll get something like this. This means that this the scalar product between two vectors B cross L and A. Okay, you can do that. Try this. And here I have used the property of the scalar triple product, all right? The scalar triple product. I have also used the property of the scalar triple product. So that's left as an exercise for you. As usual, I suggest you to do it without looking at the solution and then check with the solution in the end, all right? It's a good thing to practice with manipulating the indices a little bit, all right? With one or two problems, you'll practice this and things becomes really easy and quick. Here we have got x with Ly and Lx with y, x with Ly and Lx with y, right? So this x with Ly, I'll write it in a slightly different form. This x I call as the first component of r vector. So this is r1 and this Ly is the second component of L vector, right? That I write as L2. Okay, just for simplicity. So this just for convenience. Okay? So this is r1, what's L2? L2 is epsilon 2 jk rj pk, right? Because we said that L vector is equal to r vector cross p vector, that's the angular momentum. So L2 is equal to epsilon 2 and then you will have a dummy index here. It could be anything, it could be L, M, J, K, anything, and then rj pk, all right? That's what we have here. Now we can use the non-zero Poisson bracket from here. We see that there's a non-zero thing for R1 with Pk. R1 with Rj is 0, whatever the value of j, all right? But there is a non-zero value for R1 with Pk. So it's delta 1k. So it's epsilon 2 jk Rj delta 1k, right? So you remember that there is the summation over k here. Okay? And in all this summation, the only value that will survive is for k equal to 1. So it's epsilon 2 j1 because k has to be equal to 1 for this term to survive rj. Okay, so there's a summation over j here. There's a summation over j here because it's a repeated index, all right? But there's a problem here. There's no problem. But when you sum over j, j will take values 1, 2, 3, right? 2 and 1 are already here, so the only non-zero thing will appear for j equal to 3. So the only non-zero term in this summation is epsilon 2, 3, 1, r3, which is r3, which is equal to z. So x with Ly is z. X with Ly is z, all right? So this is actually a property of all the vectors. I have told you before, it's a property of all the vectors. Okay, and this is actually what we are doing is we are making a rotation about the y-axis. We are making a rotation about the y-axis, all right? And then the x-axis will become the new z-axis. Okay, you can, that's one way of looking at it. Right? You could also use the basic result, the earlier result, a shortcut method that we discussed in the previous class. What was that shortcut method? If you have any vector here, the component of any vector with Lj, okay, it's epsilon I j k ak, all right? So what we have here is r1 with L2. So this has to be epsilon 1 2 k rk, am I right? We are just using this formula, all right? We have seen this relation, we have derived this formula. So it's epsilon 1 2k rk. There's a summation over k, all right? But the only non-zero values comes for k equal to 3. If k equal to 1, epsilon 1 2 1, there are two repeating indices, it's 0. If k is equal to 2, then there is epsilon 1 2 2. Again, there is a repetition of index, it's 0. The only non-zero value comes when all these indices are different. All the indices of the Levi-Civita symbol are different, all right? So the only non-zero term is epsilon 1 2 3 r3. Epsilon 1 2 3 is 1, so this is simply r3, which is equal to z. Okay, so you could as well use this formula directly and obtain the answer. Okay, that's exactly what we have done here, all right? The other part you can do as a exercise. Find Px with Ly. Again, Px with Ly. We can write as P1 with L2. Right? Use this relation. Right? Use this relation. Because as we said, P1 is a component of a vector. Right? So we know that vectors all behave in a particular way under rotations, which means taking Poisson bracket. Right? Which means that the angular momentum is the generator of rotations, etc. Right? For that reason, P1 with L2 can be written as epsilon 1 2k Pk, all right, only possible value is 3, so it's epsilon 1 2 3 P3, so it's Pz, all right. So this is interesting because all the vectors behave exactly the same way when you take the Poisson bracket with the angular momentum, all right. So x with Ly was z, right, Px with Ly is Pz. Similarly, you take any vector a, okay, Ax with Ly would be the corresponding z component, Az, okay. All right, and this one again is left as an exercise. Okay, the tools that we have already discussed will suffice to solve this problem. We need to find x prime with px. Okay, x prime with px. So this is actually a coordinate transformation. X prime is equal to x cos theta minus px sin theta, and px prime is equal to x sin theta plus px cos theta. Okay. So we look here, it's x cos theta minus px sin theta, comma x sin theta plus px cos theta. So you remember that this is some sort of a rotation, right? This is some sort of a rotation between x and px, right? So let's not worry about that. Let's just look at it as a problem. So you see that x prime with px prime is also equal to 1, right? You take only the non-zero Poisson brackets, you take only the non-zero Poisson brackets, multiply the constant terms, etc., and you will get 1. Right, so we can try that. These are all exercises. Okay, these are all exercises which you can do. This is another exercise. It's nothing particularly complicated, so I'll leave it to you. All right. Okay. Here, the last problem that we'll discuss in this session. If the Hamiltonian of a system is given by h is equal to p theta square divided by 2ml square plus mgl 1 minus cos theta, find dl by dt if L is the Lagrangian. Right? So we have already solved this problem, if you remember, when we discussed the Hamiltonian formalism. Right? We need to find dl by dt. We have already solved this problem, but now we'll solve it using the Poisson brackets. All right? We'll solve it using the Poisson brackets. All right, so let's write L is p theta theta dot minus h, right? So this is one of the easy ways to do this. L is equal to p theta theta dot minus h. What do we need to find? dl by dt. Is there any explicit time dependence here in the Lagrangian? No, there is no explicit time dependence in the Lagrangian. All right, it's just p theta theta dot minus h. So dl by dt is L with h. You get an immediate simplification because h with h is 0. So the only non-zero term is p theta theta dot with h. Okay, and what's theta dot? Theta dot is simply theta with h. Right? That's the Hamilton's equation. Right? So this is true for any time derivative. The time derivative of any quantity associated with the system can be obtained by taking the Poisson bracket with the Hamiltonian. Okay, so it's p theta theta with h comma h, right? And you look at h, we need to find theta with h, so we need to find theta with h. You see that the only non-zero term comes from this because theta with p theta is non-zero, all other terms are 0. So you don't have to worry about this term. The only non-zero term comes from the first term in the Hamiltonian. Okay, so that's why I have only the first term from the Hamiltonian here. It's theta with p theta square divided by 2ml square. Okay. Now we use the usual result u comma v square etc. and then finally get to, I'll just go through all these steps. Okay, you know how to do this, you know how to do these things. We'll get a term like this, p theta with mgl 1 minus cos theta. But what do we do now? What do we do now? All right, we can make a little bit simplification because it's mgl minus mgl cos theta. So we can remove the 0 contribution because p theta with mgl is 0. Okay, so the non-zero contribution is this. It's 2 p theta divided by ml square p theta comma minus mgl cos theta. Okay, now how do we do this? We have got a cos theta here. We have got a cos theta here, right? You know that you can expand this cos theta in a Taylor expansion or in a power series of theta, etc., but that won't work here, right? Maybe that will work, we can try, but there's an easier way. Okay, this we can write, this Poisson bracket alone, right? We can write as, this is actually mgl cos theta with p theta, because I've taken that minus sign outside and cancelled it with the minus sign that you get by interchanging the arguments of the Poisson bracket, right? If you know this property of antisymmetry, u with v is equal to minus v with v. Okay, that's exactly what we have done here, right? Now we remember a result. Okay, now we remember a result that we had done in the previous class. The result was this: if you want to take the Poisson bracket with p, okay, it's equivalent to taking a partial derivative with respect to theta. All right, this means that actually the fundamental reason for this is that the momentum is actually generator of translations. All right, so if you want to take a Poisson bracket with p theta, okay, you just have to take dou by dou theta. All right, you just have to take dou by dou theta. That's exactly what we do here. It's minus 2g by L p theta sin theta. Okay, because from this cos theta, when you take the derivative, you will get this extra minus sign. All right, so we have used the result that f of q comma p with p is actually dou f by dou q. Right, so this problem I gave to you just as a demonstration of using some of the techniques that we have been familiarized with. All right, so with that, I'll conclude this session. Thank you.